MIT claims superconducting breakthrough means fusion power can be practical. Welcome. I hope you enjoy, then subscribe and like. MIT has announced a significant advancement in fusion energy research, building upon a breakthrough achieved over 2 years ago. This recent development suggests that the magnet-based design employed in previous tests is not only impressive in laboratory conditions but also holds promise for practical and economically viable fusion energy generation. The validation of this concept comes from a comprehensive report encompassing 6 separate studies published in the IEEE Transactions on Applied Superconductivity. These studies assess the feasibility of the superconductor magnets utilized by MIT scientists in their groundbreaking experiment conducted in September 2021. According to Dennis Whyte, former director of MIT's Plasma Science and Fusion Center, this advancement has drastically altered the cost-effectiveness of fusion energy, reducing the cost per watt by nearly 40 times in a single day. This significant improvement in cost efficiency enhances the viability of fusion energy as a realistic power source. Fusion, the process that powers stars like our Sun, involves the fusion of small and abundant atoms like hydrogen to generate heat that can be converted into electricity. Unlike nuclear fission, fusion produces minimal radiation and relies on readily available hydrogen atoms for fuel, rather than scarce and hazardous elements like uranium and plutonium. To achieve fusion on Earth, scientists must replicate the high temperatures and pressures found in stars. One approach involves using a tokamak, a toroidal chamber surrounded by powerful superconducting magnets, to confine and control the fusion reaction. MIT's findings suggest that tokamaks could be significantly downsized and made more cost-effective, potentially making fusion energy more feasible. The breakthrough achieved by MIT researchers involves the use of an experimental material called REBCO, enabling the magnets to maintain superconductivity at a relatively practical temperature of 20 Kelvin. Additionally, the researchers took a bold step by removing insulation from the magnet's coils, simplifying the design while maintaining functionality. This innovative approach surprised the scientific community, as it departed from conventional insulation practices. Despite this departure, the resulting magnet, weighing 20,000 pounds and capable of sustaining a magnetic field of over 20 Tesla, demonstrated potential for supporting fusion reactions with a net power output. Furthermore, extensive testing revealed the robustness and stability of the design, withstanding extreme heat caused by power shutdowns without significant damage. This resilience suggests that the magnet-based design could withstand the rigors of practical fusion energy generation. In summary, MIT's latest findings represent a significant step forward in fusion energy research, offering a more practical and economically viable approach to achieving sustainable energy generation through nuclear fusion. Thanks for watching. Please do not forget subscribe and like.